Welcome to the Chiller Training Outline Activities Part 3. In this session, we will guide you through creating effective and customized training plans for chiller equipment, ensuring operational excellence and minimal downtime. This is a diagram of a chilled plant system. It shows the different components of the system, such as the chillers, pumps, and cooling towers. The diagram also shows the status of the different components, such as whether they are open or closed. The system has multiple chillers and pumps, which are used to circulate water throughout the system. The chilled water is used to cool buildings and other facilities. The diagram shows that the system is in a healthy state, and all of the components are operating properly. The image shows a summary of the status of 4 cooling towers, CT1 to CT4. The table on the left displays information about each tower's fan status, such as whether it is healthy, auto, or off, the fan speed, and the manual override. The table on the right shows information about the tower's inlet and outlet temperatures, the butterfly valve status, and the failure status. Overall, the summary suggests that all 4 cooling towers are in good condition and operating normally. The daily checkup log for the evaporator section encompasses several vital parameters that must be monitored to ensure optimal system performance and early detection of potential issues. The monitoring process begins with recording the entering water temperature, which establishes the baseline for evaluating the system's cooling efficiency. This is followed by measuring the leaving water temperature, which must be lower than the entering temperature to confirm that proper heat exchange is occurring within the system. The saturated temperature reading provides crucial information about the refrigerant state within the evaporator. The system is currently running in auto mode with the setpoint source set to the front panel. The evaporator leaving water temperature is 6.0 degrees Celsius and the condenser water flow status is flow. The evaporator entering water temperature is 13.6 degrees Celsius and the condenser entering water temperature is 33.6 degrees Celsius. Other system parameters like the temperatures, pressures, and flow statuses are displayed. The image shows a log sheet for a compressor and motor system. The compressor data includes the number of starts, running time, oil pump discharge pressure, oil tank pressure, oil differential pressure, oil tank temperature, and IGV1 position. The motor data includes the average motor current, starter motor current for lines L1, L2, and L3, both in percentage of rated load, PLA, and actual amperes, A, and the starter input voltage for phases AB, BC, and CA. This document outlines a daily checklist for a system, likely a refrigeration system, based on the items listed. It includes checks for purge, motor, water pressure, and oil level. Each category has specific points to be monitored, such as time until next purge run, motor RLA and amps, water pressure at different points, and the oil level in the chiller's sump. The quarterly planned preventive maintenance, PPM, schedule encompasses several critical tasks that must be performed every 3 months to maintain optimal system performance. First, all strainers in the water piping systems must be thoroughly cleaned to prevent flow restrictions and ensure proper water circulation throughout the system. This is followed by a comprehensive calibration of all pressure gauges, temperature sensors, flow gauges, and other monitoring instruments to ensure accurate readings and proper system control. The chemical dosing system must also be checked and adjusted as necessary to maintain proper water treatment levels, preventing scaling and corrosion within the system. These quarterly maintenance tasks are essential for preventing system degradation and maintaining efficient operation. The half-yearly maintenance procedures focus on the mechanical aspects of the system that require attention every 6 months. The vane control linkage bearings, ball joints, and pivot points must be properly lubricated to ensure smooth operation of the capacity control system. Operating the tang operators manually allows technicians to check for any abnormalities in the mechanical linkages. The oil filter shutoff valve O-rings require lubrication to maintain proper sealing and prevent oil leakage. Additionally, any exposed metal parts must be treated with oil to prevent rust formation, which could lead to degradation of system components. These preventive measures help maintain the mechanical integrity of the system and prevent unexpected failures. The annual maintenance schedule represents the most comprehensive level of preventive maintenance for the chiller system. This includes a thorough inspection and cleaning of the condenser tubes to remove any fouling through descaling, which is crucial for maintaining heat transfer efficiency. The flow detection sensors must be checked and cleaned to ensure accurate flow monitoring. A sample of the compressor oil should be submitted to the manufacturer's laboratory for comprehensive analysis to determine its condition and suitability for continued use. The compressor motor winding resistance to ground must be measured to ensure electrical integrity. A complete leak test of the system should be performed to identify and address any refrigerant leaks. The starter wiring connections and contacts require inspection, tightening, and adjustment as needed to maintain proper electrical connections and prevent potential failures. In this image, we're looking at a maintenance procedure called descaling. You can see two important photographs here. The first one shows us a pipe system connected to a larger vessel. Think of it like the plumbing system in your home, but much bigger. You'll notice various parts like valves, which are like taps, and gauges, like thermometers. In the second photo, we can see a technician at work. They're using a special tool to clamp onto the pipe, which helps them remove unwanted mineral deposits, just like cleaning the lime scale from your kettle at home, but on an industrial scale. Looking at these images, we can see industrial equipment with yellow circles highlighting specific valves. These circles are like our "you are here" markers. The process is similar to cleaning a coffee maker at home. Just as you might run cleaning solution through your coffee maker, here we're running a special chemical through the equipment. The chemical enters through one valve, like pouring cleaner into your coffee maker, flows through the system cleaning as it goes, and comes out through another valve. The used chemical isn't wasted, it's collected in a tank or bucket and can be pumped through again, just like running multiple cleaning cycles in your dishwasher. Here's the rewritten content. This slide shows the first important step in descaling, removing the end cover or water box. Think of it like opening the lid of a container to clean inside. In the first image, you see the end cover. It's like a giant cap that needs to be taken off. The second image shows what's underneath, the water box. This is similar to removing the lid of your water bottle. To clean it properly, we need to access the inside to clean it effectively. Here we're learning three crucial steps in the descaling process. First, we wash the coils and end cap with water, just like rinsing dishes before putting them in the dishwasher. Then, we need to ensure all clamps and flanges, like the joints that hold everything together, are tight. Imagine checking that all the lids on your containers are properly sealed. Finally, we learn that this is mainly done for the condenser because it's an open circuit, meaning it's exposed to the outside environment, like an open air cooling system. We're looking at how to change an oil filter, which needs to be done once a year. It's very similar to changing the oil in your car. Let's go through the 4 simple steps. First, we turn the system to drain. Imagine opening a tap to let water out. Then, we need to be patient and wait for 30 minutes. This gives time for all the old oil to drain out completely, just like waiting for your bathtub to empty. Next comes the actual filter change. We remove the old, dirty filter and put in a fresh, clean one, just like replacing an air filter in your home air conditioner. Finally, we turn the system back to run mode, like turning your car back on after an oil change. In this image, we can see a piece of equipment with a yellow circle highlighting what we call the purge filter. Think of this filter like the lint filter in your clothes dryer. It needs to be changed regularly, in this case once a year. The purge filter's job is to catch and remove unwanted materials from the system, keeping everything running smoothly. Just like you wouldn't want to run your dryer without cleaning the lint filter, this purge filter needs regular maintenance to keep the system working efficiently. Let's talk about how to handle 2 common situations with chillers. First, when we have low capacity. Imagine your air conditioner isn't cooling enough on a hot day. If we're just a little short on cooling power, we can help by making the condenser temperature as low as possible. We do this by either adding more cooling towers, if it's water cooled, or more condenser coil, if it's air cooled. It's like adding extra fans to help cool things down. Now for high capacity, this is when the chiller is producing too much cooling. The system has something called control point offset, which will shut down the chiller if it gets too cold, like how your refrigerator turns off when it reaches the right temperature. To fix this, we can use something called hot gas bypass. Think of it as a pressure release valve that helps control the system, though it will use more energy. Train, compliance to OSHRI Standard 15. Here we're learning about safety measures, very important. First, there's a refrigerant monitor or detector in the room. Think of it like a smoke detector, but instead of detecting smoke, it detects refrigerant gas. If the refrigerant level gets too high, two things happen. First, alarms go off both inside and outside the room, just like a fire alarm system. These alarms make noise and flash lights to warn people. Second, the system starts mechanical ventilation. Imagine automatically opening windows to let fresh air in. There's also something called a purge discharge and rupture disc that must lead outside. These are like safety valves that release pressure in emergency situations, similar to the pressure relief valve on a pressure cooker. Let's learn some interesting facts about chillers. First, when you're looking at a chiller unit, the side with the control panel is always considered the front, just like the front of your TV is where the screen is. We use something called a vapor compression system, and here's how the expansion valve works. Imagine squeezing a water hose to make the water spray faster. When we increase velocity through a nozzle, the pressure drops, which makes the liquid boil at a lower temperature. Most chillers use either R123 or R514A refrigerant. These are like the fuel that makes the cooling happen. They also use special oils called oil 00022 or oil 00334/oil 00335. The number of stages in a chiller depends on how many impellers are in the compressor. Think of impellers like fans that push the refrigerant through the system. Here's a helpful tip to remember: for every 1 ton of cooling load, you need 3 GPM, gallons per minute, of chilled water supply. Let's break down this complex system into simple parts. Imagine a 3-story building where each floor helps make the cooling process more efficient. On the first floor, first stage, the refrigerant starts its journey at low pressure and temperature. It goes through the first compressor. Think of it like a pump that increases pressure and temperature. Then it goes through an intercooler, like a quick cool down stop, before moving to the second floor. On the second floor, second stage, another compressor increases the pressure and temperature even more, followed by another cooling break. The same happens on the third floor, third stage. The clever part is the economizer. Imagine it like a heat exchanger where the hot refrigerant from the top floor helps warm up the cold refrigerant from the bottom floor, saving energy just like using the steam from your shower to help heat your bathroom. The refrigerant then goes through the condenser, like a radiator, where it cools down and becomes liquid again. This liquid passes through an expansion valve, imagine a water spray nozzle, where it cools even more. Finally, in the evaporator, it absorbs heat from the area we want to cool, like how sweat cools your body by evaporating. Then the whole process starts again. This 3-stage system is more efficient than a single-stage system, just like taking 3 small steps is often easier than 1 giant leap. The economizer helps save energy by reusing heat that would otherwise be wasted, making the whole system more cost-effective to run. Thank you for participating in the Chiller Training Outline Activities module. We hope this course has provided you with valuable insights into chiller components, systems, and efficient training practices. Your commitment to understanding the intricacies of chiller operation and maintenance will significantly contribute to reducing downtime and optimizing system performance. In the next class, we will discuss HVAC chiller plant optimization. See you there. Bye.